Hello. First of all, I'm pleased with my participation in this conference, online at a national conference on science, technology, engineering, and management. In the next 15 minutes, we will cue the next story of our work, titled by Reconstruction of Fluids and Data Inversion in Eddy testing via benchmark problems and neural networks. Following the work plans, we will start this presentation with an introduction. Then we cite our MBT system problematics, which treat the benchmark validation and inverse problem. And finally, a conclusion that summarizes the work. So, by definition, non-destructive testing is a set of methods and techniques that can be used to test the state of parts and structures, especially without degrading their characteristics, particularly in the nuclear, aeronautical, and transport. Eddy testing is one of the most used techniques that allows the detection of surface and subsurface defects in electrically conductive parts. The coil is powered by an alternating current. The exciter magnetic field gives rise to an induced current in the controlled part. Even these currents cause the creation of an induced magnetic field opposite the exciter. At the presence of an anomaly, the current distribution will be modified. The aim of this study is the characterization of the defect using benchmark problem validation and data inversion by neural network. Solving this problem requires solving two problems, the direct problem and the inverse problem. Well, in the direct problem, we determine the electromagnetic phenomenon related to the sensor that generates the eddy current and the control part based on the input parameters, the physical and geometric properties of the system. In the inverse problem, the different flows, size, and shape are estimated based on the eddy current signals measured in the direct problem. Concerning the eddy current signals, here the impedance variation is plotted as a function of the sensor position. The sensor is moved along the piece with a certain pitch. The magnetodynamic formulation is solved using finite element method in order to obtain the approximate solution of magnetic vector potential and electrical scalar potential. We use these physical quantities to calculate the resistive and reactive parts of the impedance. The benchmark problems Team Workshop 15.1 and GSM 2.5 have been considered in order to validate the previous developed model. The experimental arrangement is shown schematically in this figure. A circular air-core coil is scaled parallel to the x-axis along the length of rectangular fluid in aluminum plate. Both the frequency and the coil liftoff are fixed. The impedance coil is measured as a function of the coil center position. The different parameters are listed in the following table. The objective of this section is to calculate the change of the coil impedance and to validate the previous model by comparing the results obtained by this developed model and experimental data an academic benchmark configuration. The figures show a good agreement between the numerical and experimental results for the two configurations. Now, the considered problem is a rectangular fluid part containing 5 straight fluids of different geometric parameters of length and depth. Figures show that the effect of the correct length and depth on the signature of the slopes is very apparent, where the indicator signals are strongly depend on these parameters for thin cracks. By adjusting the depth variation and keeping the same length and width of the crack, slopes of rectangular, elliptical, slope, and triangular profiles are considered for finite element simulation. Well, the figures show remarkable change in the impedance variation when the crack shape changes. Now, to estimate these defect shapes, we use an inversion technique. The null network structure used is a feed-forward multi-layer perceptron. The inputs are the variations of the impedance coil, while the outputs are the crack shapes. These impedance variations are calculated through 3D finite element simulation and validated by the experimental companion. The figures show superimpose the actual crack profiles and the results provided by the network. And finally, the accuracy of the proposed model for detecting and estimating the defect size and shape has been highlighted by comparing calculation and experimentation results. As well, simulation results confirm the effectiveness of the inverse approach to reconstruct the flow size and shape. Thank you. Stay at home. Stay safe.